sigma. Sorry, it is the difference of sigma max by minus sigma minimum by 2. That is the stress amplitude. This is the significant thing which we are going to discuss. Whenever we plot the stress strain curves, we are referring to stress as stress amplitude. Then comes the stress ratio. Stress ratio is nothing but sigma minimum by sigma maximum. Here you can see this is the sigma minimum by sigma maximum. This R ratio can be positive or negative or even zero also. When we say R is 1, it means sigma minimum is equal to sigma maximum. That is, stress remains constant, and that is called static loading, as we can be seen in whatever test we do in our labs, like testing the tensile strength of the material. And this comes under R is equal to 1, that is static loading. When R is equal to 0, that is sigma minimum is 0, it means there is only tension to 0. We are loading it, then releasing it, loading, releasing, loading, releasing. That is actually R is equal to 0. When R lies between 0 to 1, it is tension to tension. When similarly R is minus 1 implies tension as well as compression. Both will be involved and both are equal. That is, suppose if a component is loaded to a stress level of 100 MPa and then it is completely reversed to minus 100 MPa, then we define it as fully reversed cycles. Then when it R lies between minus 1 to 0, it is tension compression cycle. And these can be seen here also. Here we can see R is greater than 0. Both higher maximum stress and minimum stress are both positive. Here maximum stress is positive, minimum stress is 0, is loading and unloading to 0, loading, unloading to 0. But in this case, you can see it is varying between. Hello? Hello? I'm able to hear someone. Okay. So when R is minus 1, stress is varying from negative stress to positive stress. Oh. Hello?
Yes, sir. Yes, sir.
Okay, okay. If someone has doubts, they can always ask me at any point of time.
Okay, okay.
Okay, okay. So if stress is ranging, whenever I say stress, it means indirectly it means load. And load is varying from positive value to negative value or negative value to positive value, and both are equal. Here we call it as R is minus 1. And all the fatigue tests are done, standard fatigue tests are done for this cycle. Then when R is minus infinity implies highest stress, that is maximum stress is 0 and minimum stress is negative. And we can even see here we have a significance of the mean stress. Here there is a lot of significance to mean stress. Positive mean stress tends to bring down the fatigue life, and negative mean stress tends to increase the fatigue life. That's why we generally aim to increase the fatigue life by seeing that mean stress is as low as possible. Here we can see all these things from these curves. We can observe the same pattern. Now, how do we predict fatigue life of any component? There are generally three methods to do that. One is stress life approach, second one is the strain life approach, and third one is the linear elastic fracture mechanics. Apart from these, there is one more area, that is the elastoplastic fracture mechanics, that we will discuss later. So when we say stress life approach, it means it is a high cycle fatigue. That is, the strain rate, strain values are very, very low. So stress will become the important factor to uh, to be taken as a fatigue prediction criteria. But in case of strain life approach, the strain will be very very high, that the component fails below say 10 power 3 cycles or so, like 1000 to 10,000 cycles or so. So then if we say total life, that is stress life approach, we can say that it is a combination of strain life approach plus LEFM. That is, total life is nothing but cycles taken for crack initiation, which will be covered under strain life approach, plus cycles taken for crack growth to uh, threshold value, means greater than threshold value, where it will crack propagates to failure. That is LEFM. So total life can be treated as sum of crack initiation plus crack growth. So if let us discuss stress life approach. When I say stress here, it is alternating stress. That is sigma max minus sigma minimum by 2. Fatigue test is commonly done assuming reversed repeated cycles. So we need to determine the number of cycles to failure, number of cycles to failure with for corresponding stress amplitude. Lifetime depends on the mode of testing. So so for the same component, there will be different lives depending on mode of testing, whether it is bending or torsion or any other kind of flexural thing, or even combined loads also, and even specimen geometry also plays the major role. So how do we represent when we generate stress to alternating stress to life? How does it look like? It is actually called SN curve, and it is also called Wöhler's curve. Here you can see we have to plot stress amplitude versus number of cycles here. Here, for example, this is a sample case of this is a 400 MPa. This is mean stress of 400 MPa. Here it is a this is a positive mean stress. Blue one is the negative mean stress, and black one represents zero. As described earlier, you can see that positive mean stress is bringing the life down. For any particular stress amplitude, if you take this, for example, 600 as a stress amplitude, the life is less than 10 cycles. But if we go for zero mean stress, the life you can see it is lying around some 200 cycles. And for the same stress amplitude, if we go with the negative mean stress, it lies around some, you can see the difference around some 2000 cycles or so. So you can see the drastic difference that mean stress is playing here. So here we can, this curve can be defined in terms of an expression. It is called Bascom's equation. This sigma A, or here is nothing but S, that is alternating stress, is equal to A times NF power B. A and B are middle constants, and we can derive them here from here to the graph. NF is the number of cycles to failure. So suppose if we have these constant metal constants, and if we know the alternating stress, we can find out this number of cycles to fatigue from this kind of graphs. For most of the materials and most of the geometrical test cases, these values are available, but most of them are limited only to lab level specimen. So this is what we can observe from SN curve. Lifetime decreases with increasing stress amplitude. Existence of an endurance limit or infinite lifetime below these values, below the endurance limit. Then there is no influence of cycling rate. Cycling rate means the frequency with which load is applied. Say I can apply the load, say a cycle, some 0 to 100, sorry, minus 100 to 100. Assume that there is a cycle with from minus 100 to 100 newtons, or even stress, you can consider in any way. So if I apply that in 1 second or 10 seconds or even 1 hour, it doesn't matter. That is, cycling rate doesn't matter in SN curves. Also, if we consider the mean stress effects, as told earlier, tensile mean stress reduces the lifetime. It is because of crack opening, and compressive mean stresses increase the lifetime. That is because of crack closure. So as I mentioned earlier, that all the all the fatigue tests are done at mean stress is as zero. that is there is a complete reversal of stress from negative to positive of the same value. In that is the how tests are done, but in actual practice, certainly mean stress are not equal to zero. So we need to account for this effect while estimating the fatigue life. Whatever the equation I shown here, this Baskin equation, this is only for mean stress of zero. But we have, if we have positive mean stress, this is negative mean stress or positive mean stress, either positive or negative, in presence of mean stress, we need to use correction factors. So these are all various correction factors proposed by Soderbergh, Goodman, Gerber, and Marrow. These define here the terms are sigma m is the mean stress, as you already know. Sigma y is the yield stress or strength of the material. Sigma e dash is the effective alternating stress here. So this and all, these curves denote how conservative are we while predicting the fatigue life. If we consider this Soderbergh, this slant line represents the criteria of Soderbergh, and it is the most conservative approach. That is, um, it gives the it says that suppose if a component is supposed to sustain for some 10,000 cycles, if you use this approach, it will yield a result which is far less than 10,000, because it's most conservative and is depending on only uh, yield stress. But if we go with ultimate stress, that is Goodman criteria, it gives far closer results to the actual fatigue life. And mostly we go for Goodman criteria. And this Gerber parabola and Morrow's approach are also some of the other two criteria used to estimate the mean stress effects on fatigue life. So now we have discussed how to estimate the fatigue life for a cycle of some stress amplitude. That is, we have a maximum stress and a minimum stress. And from that, we'll estimate the alternating stress, and we'll plot the life of the component with respect to alternating stress. Suppose if we have multiple amplitude loading, that is, we have multiple numbers of maximum stress and mean stress. Suppose if you are going in a bicycle or if you are going in an aeroplane, it is subjected to random loading. So whatever we discussed earlier, it assumes only a particular stress amplitude, one stress amplitude, but we generally have multiple stress amplitudes. So in that case, I'll explain here. See, this is the case. We have multiple stress amplitudes here. This is one stress amplitude. This is the second stress amplitude. So in this case, what we need to do to estimate the fatigue life? So in this case, we use certain damage rule. Here in this case, it is called Palmgren minor damage rule. Here, damage caused by one cycle can be defined as 1 by NF, where NF is the number of cycles to fail for that particular stress amplitude. So the damage produced by n such cycles is nothing but n times d is equal to small n is the number of repetitions of this cycle. Here in this case, n1 for this cycle. N by NF, that is nothing. Suppose if we have only this cycles, we define it as damage is nothing but n1 by nf1. So since we have one more cycle here, we need to consider n2 also. So we have to sum up the damage caused by the total number of cycles, that is n1 by nf1. nf1 nf is nothing but the total number of cycles required. Here you can see nf1 is total number of cycles required for the component to fail at this particular stress amplitude. nf2 is the total number of cycles to fail required to fail at this stress amplitude. So if we have multiple stress amplitudes, we have to sum up this damage, like n1 by nf1 here in this way. This is damage for first cycle. This is damage for second stress amplitude. So total it will be n. It can be any number. It need not be 2. It can be any number, infinite number. So finally we will say total damage is nothing but ni by nf1, ni by nf5. Ni is the number of cycles of that particular stress amplitude. Nfi is the total number of cycles required to required for a failure of the component at that particular stress amplitude. So there should not be any confusion between Ni and NFi. So when we say, when this damage is one, that is 100, we can say the component has failed 100%. But in practice, damage never reaches one. See, this is the total damage. We have to sum up everything and it should be equal to 1. So total damage is indirectly is the number of cycles before failure. So this is one repetition. If we are taking a block like this, whatever I have shown here like this if we consider this as a block. See, here in this case, if we have only one stress amplitude, we can say number of cycles. But if you have multiple stress amplitudes, we have to consider it as a total block. We'll say the component fails for so many repetitions of this block. We cannot demark between failure because of first stress amplitude or second stress amplitude. We have to consider this as a total block, and total damage will be because of this block. And we have to so this damage will gives the number of repetitions of that block for failure of the total component. So let us see. Let's consider one example. So there is a certain model of ball bearings which is operating at high frequency. So it is subjected to 1 kilonewton load for 2 into 10 power 8 cycles and 2 kilonewton load for 3 into 10 power 7 cycles. So how many cycles are expected for failure? This is the question which we'll see. So the percentage time distribution is given as 1 kilonewton load is sustained for 90% of the time and 2 kilonewton load is encountered for 10% of the time. So in this case, total damage we can calculate in this way. N1 is nothing but 90% of the time, and this is denoted by 0.9 times n, and number of cycles is 2 into 10 power 8, and 10% of the cycles for this stress amplitude. Here I am mentioning it as a load, but it finally translates to stress amplitude. The total damage we have to sum up in this way, and when we take the inverse of the damage, it is the total number of cycles. I hope you got it. So in this example, we have considered the percentage time of operation of the particular load. Let us move on to next example where we will consider the mean stress effects also in terms of Goodman correction. We'll use Goodman correction in the next example. Here we have a load cycle. You can see from 0 to 800. The stress is varying from 0 to 800. Say you can consider it as MPa or something. So sigma minimum is 0, sigma maximum is 800. So stress amplitude and mean stress both are 400. This AR, it is in presence of stress amplitude in presence of mean stress. You can calculate using this term, that is 607, and NFI is obtained from this expression. So we for this stress amplitude we have this many number of cycles. Similarly, we have one more cycle with minimum stress of 220 MPa and maximum stress of 800 MPa with stress amplitude of 290 MPa. So we have one more set of number of cycles. That is, we can see for this stress amplitude, number of cycles to failure is 26,600. This 600 for this many number of cycles. We have this number of cycles to failure. Now, if we have using the Palm damage rule, we have to take the total damage in this way. See, number of cycles is 1. In second case, it is 10, and number of repetitions of load is corresponding to this cycle, and 148,000 corresponds to this cycle. So totally we have 9,510 repetitions. So there are some objections to this linear damage proposed by palm grain miner. So here sequences and interaction of events are not taken into consideration, but they do have certain influence on the life. Also, the rate of damage accumulation may depend on the load amplitude also. That we are completely ignoring the rate of damage accumulation. We are only speaking only about the damage accumulation, but not the rate at which it is accumulating. Also, experimental evidence indicates the total damage will never be equal to one for low to high or high to low loading sequence. Despite all this lacuna, because of the simplicity in this calculations and other proposed methods are also not in better agreement with the data from different tests. So because of the simplicity and availability of data, palm grain miner is widely used, even though it is linear damage rule. So for information, I'm presenting some non-linear damage rules also. Here we can see this alpha depends on the load level, which was ignored by palm grain in his rule. Now we have completed this stress life approach. Now let us move on to strain life approach. We use strain life approach only when the plastic damage, that is see in a strain value, indirect strain value is too high, that is plastic flow is considerable. In that case we go for strain life approach. So here we have to mention everything in terms of strain. Here it is also called low cycle fatigue. In general it will be less than 10 power 3 to 10 power 4 cycles. We have already seen the Baskin equation. Here sigma f by E is nothing but A, and here earlier we have mentioned as NF, here we are mentioning as 2NF. It is either way, we can mention it either way. 2NF is number of cycle. It is not a cycle, it is reverse cells. It is one cycle is nothing but two reverse cells. And similarly, to account for the plastic component of the cyclic strain amplitude, we use this Coffin-Mansion relation. Here we can see total strain is equal to total plastic strain plus total elastic strain. So all these components, sigma f, b, c, and epsilon f, these are all coefficients and exponents, and they're all standard values for certain. Some are standards particular to a metal, and some depend upon the loading pattern and as other factors like and other factors like geometry and all. So till now we discussed a predefined stress amplitudes. That is, we have a minimum to maximum or maximum to minimum, and we have it can be different types of stress amplitudes. But in general, we'll be given only load spectrum. So we need to in that case we need to count the number of cycles. See, for example, this is the spectrum of load, which we cannot clearly say what is the minimum and what is the maximum and how many cycles are present. So for this kind of things, we go for some counting techniques. In this case, it is rainflow counting technique, which is very much applicable for linear damage rule. Here we can see in the rainflow counting technique, when this difference, that is sigma yz, means delta sigma yz is the difference between these two stress levels. When this is less than delta sigma xy, we should not consider it as a cycle. When here in this example, you can see sigma yz is greater than sigma xy. See here. So we have to consider this as a cycle. X, Y, X dash. We can consider this as a cycle. We can assume this as a simple pagoda kind of thing. you can see this pagoda construction, which is very common in Japan. So this is how rain flow means when it rains, water flows from one level to other level in this way. Here also we have to imagine like this: rain flows from this level to this level. So whenever this kind of filling is done, we have to consider this as a cycle. So we'll start. So the rules of rainflow counting is like this: we have to rearrange the history to start with either the highest peak or the lowest valley. And if starting from the highest peak, go down to the next reversal, the rainflow runs down and continues unless there is either the magnitude of flowing peak is equal to or larger than the peak from which it is initiated. We have to repeat the same procedure for all the cycles, and we can just tabulate it. Here we can see this is a stress cost, stress amplitudes, sorry, stress values here. The stress is ranging from -15 to around 25, and we can just imagine rain flowing from these amplitudes in this way or in this way. I'll explain here. Here we can see when rain flows, it is making a cycle here. Means it is B, C, B star. Means this stress amplitude is less than the next stress amplitude. So we are we are counting this as one cycle. Once B, C, B dash is counted as cycle, then we can just remove this one. It will be A, D, it will be counted as A, D, E, and all. So on. Then comes F, G, F dash. Similarly, um, here FGF dash, then EH, this will be closed, then EH E dash, then this will be one cycle. Then finally we are left with A, D, and I. So these are listed here. And I'll just explain once again in detail here. You can see here, sorry, this is the actual stress cycle. Here BC is less than AB, so there will not be any cycle here. But here, so here you can see BC is less than AB. There will not be a cycle. But here in this case, B BC is less than CD. So we can make it as a cycle. We can just close this one, and we can uh, extend line from A to D. That means we have counted this as cycle and we have noted these values. Similarly, E, F, and E dash can be made as a cycle. Here, like say, then finally we are left with A, D, and A. So there are total 8 reversals and 4 cycles. These are the summary of cycles: B, C, B dash, C, B, C, B dash. Wherever it intersects is B dash. Then E, F, E dash. Once these are closed, we are left with then one more thing: G, H, G dash, and A, D, A, I, or A. Again, because the cycle starts once again from A. But there will always be uncertainty in the fatigue analysis, because if you consider so for example, if you consider an aircraft taking off from point A and landing at point B, so it will under during its takeoff, cruise, and landing, it will undergo so many loading cycles. But if you take the same flight and same pattern of takeoff, cruise, and landing, but at a different time, at different point of time, the load pattern will not be same because of the uncertainty in the wind loads, and even uncertainty in the um, other atmospheric conditions like humidity, and density and all. So there will always be uncertainty in the load history. Also, material properties. We consider the material properties. If you test two specimens taken from two sheets, taken from two different sheets produced by the same company, we'll always find that material properties are different for these two specimens, because there will be some while making this sheet, there will be so many parameters that govern them, like surface conditions and surface conditions may be different. Also, if you consider the geometrical effects like size factor, that is, the specimen tested at lab will not directly translate to the actual geometry being used in the industry. Means there will be some difference between the fatigue life estimated for a test specimen in the lab and fatigue life of the actual component. So these are all the uncertainties in the fatigue life analysis. Also, there will always be certain factors like stress risers like surface condition, size factor, load factor, temperature factor, and reliability factor. Some other miscellaneous effects also. So these are modifying factors are to be assessed from lab tests or actual prototype specimen. Only then we'll be able to confidently uh, uh, give the fatigue life of any component. So till now we have discussed stress life approach based on Baskin's relation, and then we have seen this effect of mean stress, both positive mean stress and negative compressive tensile mean stress and compressive mean stress and zero mean stress, and how we have to take care of mean stress into fatigue life, and how stress spectrum can be counted by means of palm grain damage rule. And then we also discuss this strain life approach, where additionally we have defined the Coffin-Mansion's equation here. Here, initially, during the experiments, we'll measure the total strain here, and we remove this elastic strain from the total strain to get this plastic strain. This is how this graph is plotted. So when we talk about the total strain, it is summation of elastic strain plus plastic strain. Through this, we have to approach the we estimate this strain life here. This strain life approach, and one more approach which we I'll just give the brief about this one. It is actually called fracture mechanics, and especially I'll talk about linear elastic fracture mechanics. LEFM denotes linear elastic fracture mechanics. So if you consider typical systems like aircrafts or aircraft joints, we can see all these rivet holes here, bolts and nuts. Here we can see the pin joints in rockets, and here we can see here one more example of lugs here used in the aircrafts. So all these in all these systems we are using different fasteners, which are actually the critical locations for initiation of crack. So crack initiation will take place due to dynamic loading at all these joints. In all these, like it is common to aircraft industry, shipbuilding industry, space, or bridge structures, or even automobiles also. Even if you take a simple cycle, also all this crack initiation can take place because of the dynamic loading of the uh, environment. Here, if you take example of a car, because of the speed bumps or potholes, it is always subjected to dynamic loading. Even engine vibrations also cause some dynamic loading at different parts. So these dynamic loads cause cracks at these joints especially, and they propagate. Once the crack reaches its critical value, the component cannot sustain the load and it fails. So how do we account for this failure? In general, if you consider the theory of elasticity, stress which can theory of elasticity considers failure criteria, yielding as failure criteria, but it cannot be applicable to crack rebaldi. Here we can see stress concentration can be defined as 1 plus 2a by b. If it is a circle, we say kt is equal to 3. That is stress at these point locations will be 3 times the remote stress in case of a circle. But assume that there is a crack present here. So irrespective of the crack size, whether it is 1 crack or 2 crack or 3 crack or higher also, irrespective of the crack size, we get the same value of KT. But that is actually incorrect, because KT, because when crack tends, that B represents, when it is closing, B will tend to infinity. Sorry, B tends to become 0. So thereby KT will become infinity. That means for any crack size, KT tends to infinity. So we will not be able to quantify the effect of 1 crack or 2 crack or 3 crack, because everything will be same. It tends to infinity. So we needed an additional parameter called stress intensity factor, which can describe the stress distribution at the crack location. So it can be defined as beta times S root sigma root S root pi a. S is nothing but the remote stress applied, or in this case is stress amplitude. Beta is nothing but a geometric factor depending upon the shape of the structural component. So for standard geometries, SAFs are already available. Here you can see this is actually called SCNT specimen. So most of the standard geometries, these stress intensity factors are available. We can just substitute these values here in this case, and we can find out the stress intensity factor. When I say Ki, it is opening mode of stress intensity factor. Similarly, there will be shearing mode and tearing mode also. So, but the stress, whatever stress intensity factors we obtain from the standards, are inadequate to deal with the geometries and the loading conditions used in the industrial structures because of presence of many variables. So once we have crack initiation, how do we find out the life of the component? Means what will be the life in presence of crack? For that we use there is no, after crack initiates, there will be dislocation and pore growth, and it will be it will take maximum time here. Then it comes to stable the micro cracks, then it goes to unstable crack, there is propagation, there is unstable crack growth at this location. This is the final location. This point At this point, stress intensity is called a critical stress intensity factor, and indirectly, if you consider it as a material property, it is fracture toughness. Once the fracture toughness is crossed, you can compare this to something like a ultimate stress for static load. Once it is crossed, the component will fail. So how do we quantify the life in this zone? Wo- Only when threshold crack is crossed, crack tends to grow. Here you can see crack tends to grow. So we can there are multiple theories to predict the life uh, in growing life in presence of a crack. One of the most popular criteria is Paris law, which is defined only for stable crack growth, and only it is only linear. So that is applicable to our linear elastic fracture mechanics. We are considering it only to be linear. That is, assumption in this LEFM and even in this Paris law is that the plastic region at the crack tip is very low when compared to the elastic region around it. So once we get this delta K values, and these are material parameters M and C, and this is the crack increment, is the initial crack uh, size and is the final crack size, and we can get the total number of cycles for failure. So this is how uh, failure estimation is done in presence of this life estimation is done in presence of fatigue crack. Fatigue. Um, so this to sum up, SN approach has very little precision and is over conservative, and influence of fatigue crack propagation, uh, crack thickness effect, small crack behavior. They're all not considered in this as an approach. We simply say it is a total life. We do not demarcate between crack initiation time or crack propagation time. And we coming to strain life approach, it can predict only crack initiation period, but it cannot be used for crack propagation. Also, constants of strain life relations have to be known in order to approach this approach. It is very time consuming to know these constants by using many experimental studies. And LEFM approach, it can only predict the stable crack growth period. It is not suitable for micro cracks, that is very tiny cracks, and it is valid for simple straight states and geometries. So all of them are empirical or semi-empirical and do not have sound theoretical background. They do not consider the effects of loading sequence, corrosion, and creep, etc. But out of all these, stress life approach and LEFM are the most used one. Even though there are some limitations, these are very simple and more conservative. So most of the industries they limit themselves for SN approach and LEFM approaches. And LEFM especially when they find a crack during regular maintenance. Even in aircrafts also, we if we observe very closely, we with so many cracks can be seen. But we have to see the size of the crack and the loading that crack is taking, because we cannot rule out even based on the size. We cannot rule out all the cracks to be damaging in nature, because uh, it is only after a certain number of cycles, or it is only after certain size of the crack that tend to become dangerous. So indirectly, even in presence of crack, we are flying the aircrafts, or even in presence of crack, we are using the components till certain limit, and we call that as a damage tolerant approach. How for how many cycles we can tolerate? That is, even though damage is present, we are using that component. That is actually damage tolerant approach. There is one more criteria called plastic fracture mechanics, where plastic zone size is also considered along with the elastic zone. That is, plasticity at the crack tip is also considered in this case. But so in this, the parameters used to describe the CPFM are crack tip opening displacement and J integral. This is based on the energy approach. And so since this presentation is more about fatigue, I'm limiting myself to LEFM, where it is more directly related to elastic zone. So coming to the research areas where um, the present ongoing research is going on, especially with respect to SIF, there is, as I told, so many variables are available. In case of type of crack, there are through maybe through crack, surface cracks, corner cracks, single crack, or multi-site damage also. Most of the cases come under multi-site damage, because like aircrafts and ships, there will not be a single site. It'll always be multi-site damage. We have to see how long these sustain in presence of in the presence of the loads encountered by the components. There will always be collisions of cracks. That is, one or two cracks they combine together and travel to become a bigger crack and causing more damage. So there is always a limit to that, and most of the research is going on on this multi-site damage. And there always the presence of this mode 1, mode 2, mode 3 cracks are also there. um, then coming to the geometry, we have to consider the shape, size. Even in case of holes, if there are holes or even bolts and nuts, we have to consider the number of them, pitch. If in case if pin is available at that location, or stiffness are also provided, we have to consider all these things. And in case of loads, it can be uniaxial or biaxial, bending or pressure, torsion, squeeze force, anything. Suppose if we consider a fuselage an aircraft, it is like a biaxial. Then biaxial load will be there under internal pressure, and the cracks is also matters. And type of fit also matters, like clearance, interference, snug fit. Interference fit is it tends to increase the fatigue life of the component up to certain limit. Beyond that, it doesn't matter. In some cases, if, with the extreme interference, even life is also it comes down. And preload stress can be done by even by cold working and short pinning also. Even environmental factors like temperature, humidity, and corrosion also plays an important role in determining the SIF, or indirectly the fatigue, fatigue life of the component. So these are the areas where research is being done, and there is still a lot of scope to do research. And other broad research areas, if you consider, they are gigacycle fatigue, that is greater than 10 power 9 cycles. It is assumed that earlier it was assumed that once comp doesn't fail less than 10 power 7 cycles, it will continue to means the stress, the number of the cycles to failure will be infinite. That is, if a component doesn't fail below 10 power 7 cycles, we tend to say it has infinite number of life. But it is proven to be false, because even at 10 power 9 cycles also components are failing. That is, at 10 power 7 cycles crack is being initiated, and at 10 power 9 cycles they are failing. So that is also being studied, and why it is happening. Also, there will be multi-axial fatigue. How to account for the uh, failure, fatigue crack propagation and all, because of because of loads in the multiple axes. We are only considering the single axis or uh, two axis loading, but there will always be triaxial loading also. So how to account for that fatigue? Whatever we describe in SIF and all, KIK, there is a we are mainly dealing with the K1, that is first mode. But if we consider second mode, that is shear mode, and third mode, tear mode also, there will be a combined stress intensity factor. How to account for that, and how to estimate the fatigue crack life in presence of them. Then comes the probabilistic approach. Whatever stress life approach, or fatigue, that is LEFM, which we described till now, they're all deterministic approaches, because they are all depend upon the empirical values that we get from the experiments or some studies. But one important point to be noted here is, even the SN life, the stress SN curve, from the SN curve also, when we say the component has so and so life, we are only mentioning the life at 50% probability. So if we go for higher, if you want to increase the higher probability or lower, see the probability of failure. If you want to go for low probability of failure, we have to go for statistical methods based on the available data. That is actually probabilistic approach. Similarly, in presence of a crack, how to extend the life, and how much damage can we tolerate. So by here it is done by using interference fit, or using the stiffeners, or even adhesive plates. So different studies are being mostly at the laboratory level, and they are scaling these results to the actual component by using certain factors based on some assumptions. So most of them are, see, all these studies, most of these studies, they give only approximate value of fatigue life, or in propagation. Any so there will not be any exact value. And coming to the finite element methods, because of stress singularity at the crack, it is very difficult um, to mesh the crack at that location. It is not only because of stress similarity, it is because of the geometry of the crack. A very fine crack tip has to be defined, and to capture the crack propagation, the mesh has to flow with a very fine mesh. So it consumes a lot of computational resources, and it becomes very difficult to analyze, to simulate even a test crack also. In that case, generally what people do is they go for 2D methods, but they don't take into consideration the thickness effects and all, 3D effects and all, but at least it will provide some conservative approach. So some methods like XCFEM and mesh-free methods are also, they are continuously improving themselves to be able to provide good solutions, like closer solutions to the life of the component. Similarly, we have this artificial intelligence. If we have a bulk data, that is, if you have bulk test data, like for this many number of cycles and these factors, like environment factor or loading factor or any other factor, these are my results. For second set of these parameters, means the values may change, so we'll have certain results. Like for one set of data, we'll have one SIF. Second set of data, we'll have one SIF. In that way, we have thousands of data and thousands of SIF. Suppose if you want to know SIF for a particular data, and we didn't even do experiment for that inputs, we can find out, we find out the SIF even without doing the experiment by using this artificial intelligence. Like we can say artificial neural networks. We can do that even SVMs like support vector machines or proximal support vector machines. There are many methods that we can implement. So this ends my presentation. If you have any questions, you can ask me. Hello? 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 Hello?
Hello. Hello.
Can you hear me now?
Yes, sir.
Okay, okay.
Any
So,
questions? Please give me. Sir, it's over, sir.
over. So you were able to hear till my final slide, right?
Yes.
Okay.
Sivaram sir, any participants to ask any questions, please raise. You can directly. Please unmute, sir. Sivaram sir, please unmute all the participants.
Yes, sir. Unmuted, sir.
Participants, you can ask questions. If you are not having any questions, we will end.
Sir, feedback link, sir.
Hello? Hello?
I request a participant, if you have any question, please you can interact with the resource person. If not, we will go for further.
Okay, we think that nobody is having any questions, so that we will end the program.
Okay, sir.
Okay. I'm very, sir, unmute all, sir. Sir, please unmute.
Unmute all members, sir. Anybody
Sir,
question?
feedback link, sir.
Please.
Feedback link.
Yes,
We will send it. We will send it. So I'm very thankful to Dr. Hitendra.
Rajini?
And I will thank all the participants who has participated in this program, participant and Hitendra, mainly
you, sir.
Hitendra sir. Thank you very much.
Thank you, sir.
Thank you very much, sir.
Okay. Thank you.
Thank you, Hitendra.
Yes, sir. Thank you, sir. Thank you for the opportunity.
Okay, thank you.
Okay, thank you.
Okay, you can.
Okay, sir. I'm leaving.
Okay.